Okay, here we go. So welcome after the break. So we are finding transformation matrix between frame 2 and frame 1. So in which we already have found the rotation matrix and displacement vector. So now we can write this HTM in a full form. So first, our first this part. This part is our rotation matrix. We found over here. Okay, this is our rotation matrix. And second part, this one, 3 components. This is our let me write down here, D2 to 1, and this is our rotation matrix D2 to 1. So this D2 to 1 is a position vector which is pointing from the origin of frame 1 to the origin of frame 2, and we found it over here already, right? L1, 0. Okay, we have found HTM 1 to 0, HTM 2 to 1, and now next we find last one 3 to 2 HTM, because only then we multiply them backward and then we find the HTM from 3 to 0. So in this case we have to find 3 to 2 rotation matrix, then D 2 to 3 to 2 displacement vector, and then there are 3 zeros and there is 1. So that is our HTM for the last 2 frames. Let's go to our kinematic diagram and see how our last 2 frames looks like. Here we go. We have frame 2 in this direction and frame 3 in this direction. If you look at the frame 2 and frame 3, what do you see? They are displacement by this, there is no L2, actually this D3, and they have the same rotation, because x2 in same direction x3, y2 in same direction y3, z2 in same direction z3. So what will be the rotation? No rotation means identity matrix. Identity matrix, right? So
displacement vector will be L2, 0, 0.
Let me go one by one, step by step. Let me go step by step. So first we have to find D3 to 2, and we already decided that our 3 to 2 is identity matrix. Why? Because they have the same direction. Because frame 2 and 3 are in same direction, so it will be identity matrix. No rotation. Identity matrix means no rotation. Clear? No rotation. Okay, this is done. What about the displacement? So let me redraw our frames again over here. So our frames 2 and 3 looks like this. I think this is our x2, this is our z2, and here we have same direction x2, x3, and z3, and that was our y2, and that is our y3. And displacement vector is from here to here. We call it our joint variable D3. That is D3, right? Changing. It is. So this example is, if you look at the kinematic diagram, this example looks like a human arm, like this. Human arm, right? We are here, and I just put it here like this. And here, let's say we have a prismatic joint. By this arm can go up and down, and then we have that is fixed. That is not a revolute joint. This is prismatic joint. This is only one revolute joint. So this is I mean, if this rotates, we have only one revolute joint, but this is not revolute. This is prismatic. So this can go up and down. We can make any kind of robot, but the steps will be same. You have to follow all these steps. So we are here. Okay, here. So okay, we are trying to find the D3 to 2. What is the meaning of this? First, I have to understand what is the meaning of this. It's meaning that the displacement vector, this is a displacement vector pointing to origin of frame 3, pointing to origin of frame 3, and starting from point 2, starting from point 2, from origin of frame 2. That is clear. It is starting from here and it is going to the origin of frame 3. This is our vector that we call it, what do we call it, B and P. So, this is a vector BP. Okay. So, what will be that? So, this vector BP, if we see, it is going only in the z direction. It is not going in the x direction. It is not going in the x direction, not going in the y direction. So, it has only x component will be 0, y component will be 0, and that will be not L. There is no L2. It is D3. Only z component will be D3. So, what does it mean? X component will be 3 to 2, y component 3 to 2, z component 3 to 2. Please revise the first 2 lectures again and again, because that there is chapter 2 of J. Craig book. J. Craig book, it explains in very detail. I make my notes from there. So, you can find much, but first read my lectures carefully, my lecture notes, and after that you can read the book J. Craig, chapter number 2. So, this is the situation, right? So, we found our this D3 to 2 vector, which is 0, 0, D3. Got it? So, this is our rotational matrix, which is identity. This is our displacement vector, which is 0, 0, D3. So, now we can build up. Now we can make STM 3 to 2. Let me write down here. So, your rotation matrix is identity matrix. It will be 1, 0, 0, 0, 1, 0, 0, 0, 1. Displacement vector will be 0, 0, D3, and last row will be 0, 0, 0, and 1. Clear?
My teacher called D3 and in the previous HTML called L1.
This is a variable. You can give any name. You can give it to your name, no problem. A, B, C. Okay. You can say any name, but why we call it D3? Because this is a joint variable, and joint variable we write like theta for the revolute joint. We write like this, and D for our prismatic joint. This is the notation we see in the first lecture, prismatic joint. So, this is the notation we use. D3, D for the prismatic joint, linear joint, D theta for revolute joint. So, that is why I say that because this is moving like this, up and down. Okay? So, I call it D3, but you can say it L or anything. But note that this is the not fixed. It is a function of time. Why? Because it is linear joint. Linear joint is changing in position, not fixed. But what about this one, L1? It is fixed. It is not changing. Right? What about the theta? It is changing. It is variable, right? It is theta to t, like this. So, you have to be careful, because when you derive the differential kinematics, you should first understand what is the fixed value, what is fixed variable, what is the variable which is changing with time, because you have to do the different derivatives with respect to time. So, derivative of the fixed variable will be 0, but the derivatives will be of the time function will be differentiable.
But in problems, it will be not D3, there will be some kind of variable.
It is variable. If it is fixed, it means that if it is fixed, it means that it is link length. If it is not fixed, it means that it is joint variable.
But instead of this,
We can call it L2, L3, anything. Not L2. We call it L3, A3, B3, C3, Z, anything.
yeah, but like if L1 is 10, like for example.
Yes, that is fixed. L1 is fixed, but D3 is changing.
Changing, so we can't substitute it with a number.
No, because it's a variable. Variable.
And so how do we distinguish them? Change it or fix it?
If it is joint variable is always changing. If it is link length is fixed. Right? Link length is fixed. See, my arm. Can I change this length? Cannot. Right? For a prosthetic limb. This length I cannot change, but this angle I can change. Right? So this is joint variable, this is link length. Okay, so we made these 3 HTMs. Now we are in a good shape that we found our 3 HTMs manually for this example. What is our next step? Yes, multiply all these HTMs, multiply HTMs to find final HTM. To find final HTM, because that is our forward kinematic. Final HTM means forward kinematic, right? So let's do it. So our HTM will be this is our final HTM 320. Okay, we can get it by multiplying all these HTMs. Okay, you cannot do it manually. Paper, but I did in the morning. I multiplied them in Python. Let me show that. I multiplied them in Python. I think I have script. We multiply all these 3 HTMs and we get this final HTM. So this final HTM is our 320. In this this part is our rotation matrix R320, and this part this one D320. So what is the meaning of this? What is the meaning of this? Physical meaning, like what do you understand from this? So this D320 will show that the position of end-effector.
Related to base.
Yes, position of end-effector relative to base. So base frame is your 0 frame, end-effector frame is your 3 frame. So this is the meaning of this, right? Similarly, this meaning is the rotation of the end-effector with respect to the base frame. So this is what we finally calculated. I think I have the code. Have you installed Anaconda in your computers?
Yes.
So someone has installed, some not installed. Please install the Anaconda. You can use the Jupyter notebook, and it is very easy to make your Python codes. Let me where is that? Not here.
Java titled notebook 8 hours ago.
No, I wrote, I saved it, that, let me check where I saved it. I saved that code, maybe in the lecture notes, let me check. Over here, okay. So I want to show you this, I just want to show you that code. How to go there? Let me copy it. copy from here to that folder. Here I have many Jupyter Notebook projects here. Now I can open it. Oh no, not this one. Okay, I think I did not save it. I just copy it. Copy the result. Okay. Just you code like this. You already have HTM, these three HTM. You multiply them in using symbolic form of the MATLAB or symbolic toolbox of MATLAB or symbolic form of Python, and you can get the result like this. So you can do it manually, but it's a very long process. So you can use the software, right? So, okay. So what we are interested? We are interested in this position of our end-effector with respect to base frame, and we are interested in the rotational matrix of the base end-effector with respect to base frame. This is our final result. So this completes our forward kinematic model, right? So what are our next step? Our agenda today, I think we cannot complete it because time is very short. So we done this one, inverse kinematic. Okay, let me go to differential kinematic first. So for this example, so this example is very important that you can understand all the steps. Okay, this one, then we can make let me copy it and say step 3 is derive the differential kinematic model. Because we got position, we can get the derivative as easily. So what is our three positions? Our three positions are, we can get it from here. Okay, L1 cos of theta 2 minus D3, this one, right? So this is our three positions are like x 3 to 0, y 3 to 0, and z 3 to 0. So z will be 0 because we are considering only 2 dimensional. So we have only these two. So we call it x position and y position, right? This one, this is the x position, this is our y position. And simply we can x position mean the end position of the end-effector with respect to base frame, and y position of y axis, position of the end-effector in the y axis of the base frame. Can I remember it? If I cannot remember, I can take a picture and then. Okay. So let's write down over here. So that is L1 cosine of, okay. Now you take care of the time derivatives. Because now you have to take a differentiation. So the x will not be fixed. X is a variable, time variable. The position of end-effector is changing, right? So that is L1. L1 is not a time, it is fixed, right? Cosine of theta 2, that is also time variable dependent, right? Minus D3, that is also time dependent, and sine of theta 2, that is also time dependent. This is your x position. What is your y position? That is L1, is it fixed? Sine of theta 2 with time, plus D3, that is also time dependent, cosine of theta 2, that is also time dependent. So this is your position of the end-effector. This is your position of end-effector relative to base frame, right? Have I started recording? Oh, yes, okay. So this is the position of end-effector. How you get the differential kinematics? Differentiate, right? Differential kinematic, you get the differentiate with respect to time, and you get x dot y dot. That is what you want, right? So how you will do it? Okay, it's easy because you already have x. Let me call it equation number 1, equation number 2, whatever. Let me call it maybe 1, equation number 2. So equation number 1 you differentiate. What do you get? X dot. So that will be like okay, minus L1 sine of theta 2 and theta 2 dot, because this is a time derivative, right? Okay, now here the issue. You have two variables, right? So use the product rule of differentiation. Apply product rule of differentiation. What is that? Daniel, you know?
Yeah, in this case you have minus d3 cosine theta 2 by theta 2
Right.
dot.
Yeah, let me just write down first. First, if you have two functions, which is a function of time also, and that is also a function of time also, okay? So then you do it like you take the derivative of first one, write the second one, plus you take the first one as it is and take the derivative of first. So this you will apply over here, right? So Daniel already started applying. So what is that?
Minus d3 cosine
Yeah.
theta 2 by theta 2 dot.
D. Okay.
I started with theta.
Okay, let me do it like this. First we will do it like this. Cosine of theta 2 and theta 2.
No, if we have d3 dot, it would be minus d3 dot and sine.
Okay, first we write it like this. So we write it first as sine of theta 2, like this, okay? This first is first as it is. Then minus, because this is minus, outside is minus. So we write it d3, and that will become a cosine of theta 2 dot. Good. So this is our first derivative. Second derivative will be similar. So y2 dot will be equal to, same way, we can L1 cosine of theta 2 dot, and then here again we say, let's say d3 dot, and then cosine of theta 2 dot, and plus d3, right, minus sinus theta 2 dot. Right, good. So these two equations we get by differentiating equation number 1, equation number 2. Clear? So let's say this is equation number 3, equation number 4. Okay, now you want to write equation number 3 and 4, write equation 3 and 4 in matrix form, so that you can see the Jacobian matrix, and then you can see the velocity of the joint variable, velocity of the, on left hand side you have velocity of the End-Effector. So you can write this in the matrix form like x dot and y dot on this form. On right hand side you have the theta 2 dot and d3 dot. So what will be the entry? What will be the matrix? So you can see that will be the matrix, because we have theta 2 dot this term and this term we can combine. So that will be minus L1 sine of theta 2 and minus d3 cosine of theta 2. That is theta 2 term, theta 2 dot, and theta 3 dot term is only minus sine of theta 2. Right? We are writing equation 3 and 4 in matrix form. What will come here? So, this term and this term will combine. So, that will be L1 theta 2 and that will be minus L d3 sine of theta 2. That is x2 dot term and d3 terms only this one, right? That will be cosine of theta 2. That is d3. Good. What is that? Jacobian matrix multiply with the Q dot equal to x dot. Same as we studied last time, that on the right hand side we have the Q dot, which is the velocity of the end-effector, velocity of the joints, velocity of joints, and this is the velocity of your end-effector, and the matrix which is linking these two quantities is Jacobian matrix. That's great. So, this is your forward differential kinematic. Easy. So, it means that first you find the forward kinematic and find the position vector, which is d2, d3 to 2 in this case. In this case, d3 to 0. First, we find this one by multiplying all the HTMs, and from there you have the x term, y term, z term. Z term is 0 in this case because we are dealing with the planar robots. But if in the next classes, like when you study the robotics manufacturing 1, we'll study the 3D or 6D manipulators where you have the all x axis, y axis, z axis, and then the angles in x direction, y direction, z direction. So, in this class I make it simple that we just studying the planar robots, planar manipulators. So, from here you get these two equations, x equation and y equation, and then you differentiate with respect to time. If needed, you can apply this product rule, and then you simplify these equations in the matrix form, and that will give you the forward differential kinematic. So, still we have time. Let us go to the next step. Our next step is to, we have done this one, we have done this one, we have done forward kinematic, we have done differential kinematic, and not this one. Let's do it. Inverse kinematic. What is inverse kinematic? Sorry?
We multiplied HTMIs and we got forward kinematics. When we multiplied the final HTMI.
Final HTMI we get already, that is forward kinematic.
It's called
Forward kinematic.
When we derive the displacement, it will be called, and when derive displacement, and
It is called differential forward kinematic.
but we only took the displacement.
Okay, let me calculate in differential forward kinematic.
But here we only took the displacement part, right? We don't take the rotational part.
Yes.
So only the part of it. And
Because we consider only the velocity model, velocity component, not the angular velocity. The only linear velocity part. X velocity, y velocity, z velocity. Z is 0.
when we differentiate, it will be called
It will be called differential forward kinematic.
differential.
The green one, differential forward kinematic, right? So now we go to the inverse kinematic. That we make it down. So inverse kinematic model. So that is the second step. Inverse kinematic model means that you have you have your position and you find some function which will give you the joint variables. You have position of end-effector and you have to find this function, that function g, which will give you the position of your joints or joint variables, right? It is inverse to the forward. What is forward? Forward is this one. You know your joints, you find this function that will give you the position of end-effector. Now we are considering this one. You know this one and you want to find q. So you find this relationship. What is that? What is the g function? So let's go to, okay, first our kinematic diagram. This is our kinematic diagram, as I know. So we'll use this again in our inverse kinematic. So what is our goal? Our goal is that this point P, that we write point P, its position in the base frame is given. Base frame is x0, y0, and link length L1 is also given. And what we have to find? Joint variables. How many joint variables we have? Theta 2 and d3, right? Let's go to our inverse kinematic. So here it means that we have to find theta 2 and d3, and we are given x position and y position of the end-effector. This is known. This relation is known. Also we know the L1 link length, because that is fixed one. Link length L1 we know, and we have to find these variables. So let's what method we studied last time for inverse kinematic, if you remember? Yes, graphical geometric method, right? Graphical method. I did it at home. I think I should. Okay, let me. I did it just last night at my home. Okay, let me draw the kinematic diagram first. So not kinematic diagram. This time we have only this x0 axis and y0 axis, and we have our this L1 link length. Then we have our this end-effector, right? This is our robot. So this point has coordinates x and y in with respect to this base frame, right? It means that this point is x and this point is y. This is y, this is x. So let's draw a drawing. So what is graphical method? You make some triangles on top of your kinematic diagram. These triangles can be right angle triangles, can be not right angle triangles. If they are right angle triangles, then your life will be easy, that you can apply Pythagorean theorem, sine, cosine, this kind of thing. But if it is not right angle triangles, then you have to apply the law of cosines and maybe some other trigonometry to find the angles of joint variables. So if this is the case, so we can make this triangle first of all. That we got O, let's say A and P. So in triangle, this is right angle triangle OAP. Okay. We know this x, this is y. So can we find this angle? Let me call it what do you call it? Let's say anything. Let's say beta. So we can find this angle. Tangent of beta is equal to y over x. From here you can find beta is equal to okay. You find this full angle, and this L1 you know okay. Also you can find this one because this is right angle triangle. So you can find this x square plus y square under root. Right, because this in triangle OP will be equal to this one. Okay, if you get this OP, so and this length is d3. Your giant variable, right? Moving in this direction. So it means that, and this angle is 90. Okay. So can you find this angle? Let me call it alpha.
We can find it using L1
Yes.
and 90
We can get alpha using from this triangle, right? So then cosine of alpha. Cosine of alpha will be L1 divided by x2 y2, right? So from here we can get alpha cosine inverse of, because we know L1, we know x, we know y. Yeah, under root. So we can find this one, right? Okay. And if we know this one, what is our giant variable in this diagram? Our giant variable is this theta 2 and d3. Finally, we want to find this one, right? We want to find this one, we want to find this one. So it means that you got this angle, you got this angle. So you can write it like this: beta is equal to. So you can write it like beta is equal to alpha plus theta 2, and from here you can get theta 2. Beta minus alpha. So this is your one giant variable you find. Remaining is d3. For d3. What you can do? Let me check it. My lecture notes. Okay. For D3 is also easy because you already have this right angle triangle O. Let me call it BP. In triangle OBP, what you do? You can write it like tangent of alpha is equal to D3 over L1. Right? So from here you can find D3. So from here you can find D3. D3 will be equal to L1 tangent of alpha. This is your second giant variable. Equation number 2, equation number 1. So 1 and 2 gives inverse kinematic model. Why? Because in theta 2 we know alpha in terms of what? This one. Because we can calculate alpha using L1, x2, x and y. No problem. We can calculate beta using L1, which is beta. This using using y axis and axis position, we can calculate beta from here. and then we can calculate theta 2. Similarly, for D3, second variable, we can calculate alpha from here, and then we can multiply this one. And so that's all. Only equation number 1 and 2, along with equation number this beta and equation number alpha, we can calculate these giant variables. Theta 2 what?
No, we're trying to find theta 2. We find alpha and beta, and now we know theta 2.
Yeah, because we first to find this. Our goal is to find theta 2, but theta 2 we cannot find from. We can find some other way, but this is one way that we first calculate beta, then we calculate alpha, and then beta is equal to alpha plus theta from this triangle, and then we can calculate theta 2 from here. So now you see that the theta 2 and let me make more space. So theta 2 is your theta 2 variable and D3 variable. That we, if you write in the complete form, so that will be equal to, first we write the beta, so first we write the alpha, okay, this one and this one. Okay, beta. First we write the beta is equal to tangent, I am writing the complete form. Theta 2 will be this one minus alpha cosine inverse of L1 over x, this one. So this is the complete form of the joint variable, right? Second, D3 L1 tangent of alpha. What is alpha? Alpha is tangent of cosine inverse of L1 x2 y2 under root. So see what you get. So this is a inverse kinematic model where you can write it like this: Q in terms of x and L, L1. L1 is link length, it is fixed, but x is your x and y position, that is your x, and Q is your here is a vector. It consists of theta 2 and D3. That's all. That is what we call it the inverse kinematic model. Right? Any question? So this G is this function that tan inverse y over x minus cosine this to this, and here so G is this function which is relating the position of the end-effector and the joint angles. So we done our third objective. So still we have 3 minutes, 5 minutes. Okay, I hope we can finish. We done this one. Okay. Okay, I turn it green. Last, differential inverse kinematic model. So for that, let's go at the end. So we have calculated forward differential kinematic over here. Okay. This is forward differential kinematic. What is that? Over here. So let me write in a good way that I can copy this one. So our last step is 3 and then 4. Step 4. Inverse differential kinematic model. That is our last step. So let's do it. So we have forward differential kinematic model. What is that? That is just over here. X dot is equal to j q dot. J Q dot. This is our forward differential kinematic, and here we want inverse differential kinematic, right? So if you have this relationship, forward differential kinematic, can you find like so what is inverse differential kinematic? Means that, okay, first let me tell you this one. So this is, we already see that if it is a function which is, if you know the joint speed, if you know the joint speed known, you can calculate end-effector speed or velocity, right? This is your forward kinematic model, forward differential kinematic model. And what is your inverse differential kinematic model? That is inverse. That if you know the speed of your end-effector, you can calculate speed of your joints. Speed of end-effector, in this case it is known. Okay, and you can calculate your speed of joints, joint speed. That is inverse kinematic. So we can, once we have the forward differential kinematic, to get the inverse differential kinematic is just very easy task. Why? Because we have this kind of relationship already. So what if we get, how we can get from this equation?
We need to multiply by inverse matrix of Jacobian from the left.
Good, like this. Just inverse your Jacobian matrix, and that's all.
The one that we get previous.
Huh?
The one that we get previous.
So, for example, if anyone, like you have y is equal to ax, then what is x? A inverse y, right? So, same way you have x dot is equal to j q dot. So, what is q dot? J inverse x dot, right? That is just your, so just by inverting, just by taking the inverse of J matrix, we can get inverse differential kinematic. So that's why I say that it is easy. In this case, it is easy that you can get your q dot only by inverting S dot. Inverse of Jacobian matrix. So you can do. You know already this is your Jacobian matrix. Okay. This is just 2 by 2. Even you can do by hand calculation. What is inverse? So you know that inverse of Jacobian matrix is what? Determinant. Sorry, not determinant. It is adjoint of J divided by determinant of J. This is the general formula for the calculating the inverse of any matrix. You can use MATLAB or Python to calculate the inverse, but if it is 2 by 2 case, you can also do, like if it is, for example, let's say J is 2, 3, 4, 5. So then you can get J inverse just by I think replacing the place, and this is minus 4, and then here multiply 10 minus 12, Okay, that is minus 2. So 1 over minus 2, then 5 minus 3 minus 4 2. That is your inverse if it is 2 by 2 case, right? But if it is 3 by 3, 4 by 4, you can calculate using software, MATLAB or something. Okay, I done it finally. So we can make it like green. Okay. So we have done all 5 steps. So I try to explain in much detail, and we also recorded this video for you. Please watch it again and again. You will get full understanding of what we have studied so far in 6 lectures. And after midterm, we'll start the new topics. So good luck for your midterm. Next time we'll have the midterm, not in this room because this room is very small. So we'll go some bigger room. Let me stop the recording.